A very good evening to all participants and Professor Debabrata Das. So it's a great pleasure that we have got Professor Debabrata Das, who is a chairman of IEEE Bangalore section in 2007, and he is a professor in IIIT Bangalore. So thank you, sir, for giving us time and opportunity to hear you in this platform. He'll be talking on a very interesting topic today on network slicing for 5G and beyond MAC layer. Before that, let me read out a brief bio data of Dr. Das. Professor Debabrata Das is serving as professor at IIIT Bangalore. Before joining IIIT Bangalore, he had taught at G.S. Sanyal School of Telecommunication at IIT Kharagpur and later at Kirana Networks in New Jersey, US. He is co-PI of a project from Ministry of Electronics and Information Technology, Government of India and Cognizant Technologies Limited on Smart Home and PI of a project from Tejas Network on network node reliability. He was PI of multiple sponsored projects from Intel, Hewlett Packard, Microsoft, Motorola, Research, Nokia, Government of India on areas of broadband wireless, MAC, quality of service, energy saving. IMS, his main research interests are IoT and wireless access networks, MAC layer. MAC, quality of service and power saving. Dr. Das received his Ph.D. degree from Indian Institute of Technology, Kharagpur. He has more than 160 peer-reviewed papers in different transactions, journals, and international conferences. Dr. Das has received 4 Best Paper Awards. He has 3 US Indian patents and 10 more are under review. He and his wireless network team has contributed 3 ideas to IEEE Broadband Wireless Standard. He has received Professor K. Sreenivasan Memorial Award 2017 for excellent teaching in the areas of telecommunications from IEEE. Dr. Das is a recipient of IEEE Region 10 Outstanding Volunteer Award 2020, Global IEEE MGA Achievement Award in 2012, and Outstanding Volunteer Award IEEE Bangalore section in 2008. Professor Das is a Fellow-IEEE, Fellow-IE, and a senior member IEEE. He was recipient of Hewlett Packard Endowment Chair Professor in IIIT Bangalore from 2003 to 2008, 2010 to 2012, and 2014 to 2017. Professor Das was chairperson of IEEE Bangalore section in 2017. Professor Das is a board member of IIIT Bhubaneswar also. Professor Das is a technical steering Empower committee member of multiple departments of Government of India and Government of Karnataka. Professor Das was the Dean Academic and R&D of IIIT Bangalore from 2014 to 2017. Thank you, Dr. Das. You can now take over. And to the participants, he is a close friend of mine also. Let me share with you. And I'm very much proud of him. Thank you.
Thank you, Professor Susmita Das, for such a kind introduction. Let me tell that you are one of the brightest students of our time, if I remember. You did so well, and also Professor Deepthi and other colleagues are there and Rourkela doing so well. I am also equally proud of you all, and thank you for giving me time and opportunity to speak. And I also want to thank all the organizing committee members to organize such a pertinent workshop on this futuristic wireless communication and IoT, 5G and beyond. Before I come to the topic, I want to thank also the patron and the director, Professor Animesh, which was very kind person by heart. So convey my regards to him too. Okay, so with these lines, let me go back to the top my slides, and I request any participants, if you have any questions, you can ask me, or you can write it down. I will find it out where it is, then I will try to give answers to those questions. Thank you again, Professor Susmita, for inviting me, and I hope and wish a grand success of these workshops.
Thank you. Thank you, Dr. Das.
Let me go to my slides. Are you able to see the slides?
Yeah.
Thanks.
Yes.
Okay, so before I go to my topic, let me first appreciate the workshops, this 5 days long nice workshop with so much nice speakers you have already invited. Out of that, 2 of them are the galaxies of NIT Rourkela, Professor Prashant Mahapatra and Professor Ashutosh, who was once graduated from W department, if I remember. So both of them are doing very well, and also we always look forward to both of them to listen. And particularly Ashutosh, when speaks on the security on 5G, whole world listens. So it is a pride of NIT Rourkela.
Thank you.
Coming to the point is this futuristic wireless communication and IoT, 5G and beyond. This futuristic wireless communication is in a very aggressive mode of research going on, which we are many speakers and also participants are talking about that in this workshop. But coming to the point, IoT is there. So let me give an understanding about the IoT to the people who are being attending here. You see, when this 2G, 3G till 4G, it was a majorly machine to machine communication was not there so much. It was majorly human being to human being communications or human being to the machines communications. Let me make you understand that if I am talking, I want to talk to someone, I just pick up my phone, or now I am doing a video conference with you people. This is a human to human communications. But at the 4G, middle of the 4G, when it was evolving, and when the 4G advance came, at that time, people thought a lot of machines to machine communication is very much required. So then people started incorporating a lot of IoT related things. But there are a lot of issues and also related technology research issues people need to understand with respect to IoT before I go forward in this network slicing. So let me ask the participants that how many IoT devices they are expecting on this network, which is called internet presently, because telecom network is slowly merging over the internet because voice over IP, video over IP is so popular now. So that is merging on it. That is another big topic to discuss. But internet is going to be our backbone for communication. So if you think of how many IoT devices, then the picture will be much clearer. The main topic is futuristic wireless communication and IoT on 5G and beyond. So these questions once was asked to me by a student, and then I was in the class. Then I was doing some calculations with the student, with the help of the students. So then I asked them, what do you think about the IoTs? How many numbers of IoT devices will be there over the next 10 years, say? Or maybe 10 years or 5 years, 10 years, 15 years, 10 to 15 years. So it's a very simple calculation. They said, sir, per human being, if there are 100 IoT devices, for an example, if you have a smart car you are driving, inside the car there will be around 30 to 40 IoT devices. One is taking care of your air condition, one is taking care of your brakes, one is taking care of your engines, one like that. There will be at least 20 to 30 IoT devices taking care of you. There will be another hundreds of IoT devices for other kind of things like air pressures and all kind of things, but taking care of the human being inside the car. Then if you come home, there is a smart home for you, there will be another 20, 30 IoT devices or more than that. And if you go to office, there will be another 30, 40 IoT devices starting from your light, air conditionings to your all kind of things. So if you look at per human being in an urban area, it will be 150 to around smart IoT devices, and in the rural places there will be 50 IoT devices. They may not need so many IoT devices for their personal use. I'm talking about the personal use. I'm not talking about the industry and all. So in an average, if it is 100 per user, there are 7 billion human beings on this earth, 7.5 billion. 7.5 billion multiplied by 100 is 700 billion IoT devices will be there in 15 to 20 years. Can you imagine? So now we have only mobile handsets of only 4.5 billion because we are 7.5 billion human being and mobile handset of 4.5 billion to 5 billion. In 4.5 billion to 5 billion mobile handset, we have so much call drop. We have so much of delay, throughput problems and all. But just think of if 700 billion devices come up plus this 5 billion of your laptop, IoT device, mobile handheld device up all together 5.5 billion, but 700 billion of IoT, what will happen to the network? So in front of us, there is a huge challenge as 5G is coming in and 6G will be there down the line 7 to 8 years or 10 years from the now. So what should be my work on the access network and the backbone? So please, those who are in the networking communication side, please try to understand in front of you this IoT and the user equipment, which is mobile handsets, will bring in huge challenge. That not challenge of different applications, services on the network. Having said that, let me go ahead that how to solve these problems on these networks by giving this topic this committee of organizing committee has made. There's futuristic wireless communications and the IoT. So now this network slicing is one of these strong contender to solve some of those problems, which I told to you. And myself, you have already, Professor Smith has said, I am now recently got in the last week a project, which is I'm a project director of Technology Innovation Hub, TIH of DST on advanced communication systems. We are going to develop. I will talk about one slides on here when I'll be in my talk later on. And also I had the networking communication research lab in IIIT Bangalore. So my talk will have an introduction, quick introduction, one slide, then part one. Why we need network slicing in 5G and 6G. And I only talk about the concepts, the fundamentals, very fundamental, why I need it. If you understand this, then how to achieve the network slicing, if you understand these two parts, part one and part two, then the part three is that there are hundreds and hundreds of research problems we have to solve over time. And it is a long, in the summary I have said, it will take how many years to solve this problem. So first, let us try to understand the concepts and I'll go to very basics and fundamentals of the networking, and I'll make you understand that where we are heading for. And then I'll talk to you about the part three research done in our lab in IIIT Bangalore, and the new lab which is coming up is Technology Incubation Hub in present and future network slicing and such, and the summary. So now, if you look at 5G has mainly following three broad services, which you might have heard from other speakers. Let me quickly touch base these three. Then one is called enhanced mobile broadband, which is an extension of present 4G advanced, which you are using on your mobile handsets and your laptop and all those things by making these communications. Next one is called massive machine type communication. You see, this massive machine type communication is nothing but MTC or IoT, but this massive word is come in. This massive means I gave you the calculation that if there are billions of these IoT devices or machine type communications comes onto the internet, what will happen? And only these names are not enough, but critical communication, which was not there previously, ultra reliable, low latency communications. What is ultra reliable means not a single packet can be lost, because wireless is very prone to loss of informations because the bit error rate is high, and low latency, very, very low. You see, when I'm speaking to you over a 4G phone, my end-to-end delay is 150 millisecond in 4G. If you look at, and 5G wants much less. But here people are talking about the latency of 1 millisecond or 2 milliseconds, which I'll give you some examples when I go into my presentation. So low latency, but highly reliable, these contradictories. So these three things, this above broad range of services above these three will demand performance from the operator. Operator means your internet service provider or a telecom provider. Examples starting from 1 millisecond to 2000 milliseconds. So much of variance. 1 millisecond to 2000 milliseconds. 1 millisecond means driverless cars. 2000 millisecond maybe your email. You are sending a mail from to your friend. 2 seconds. 2000 millisecond means 2 seconds. This delay is okay. So in between, there will be so many applications. So much variety means 2000 times of delay here. But these three applications will demand these kind of things. So if they demand, how to achieve that? So network slicing is one of the strong candidates to meet the above. So network slicing is a technology which is coming up, which is going to meet the above. But why I need network slicing? That will be my part one, and part one will be explaining that. What are those research problems and why, fundamentals of that. So first, let us try to understand end-to-end architecture of 5G. What is the end-to-end architecture? Many students thinks that, many participants thinks that end-to-end means 5G means here I am on a 5G network, you are sitting on a 5G network, from here to you is all 5G. It's not true. In between there is a huge optical networks, because from I am sitting at here, and the destination is in Rourkela, which is close to 1,500 or 1,800 kilometers from here. So this in between there is an optical network. Only last 1 kilometer is only 5G. So we need to understand, if I want to meet this kind of delays, then how to have this end-to-end architecture of the 5G. I'll give you some practical examples of that. Secondly, what are the elements affects the performance of the delay, throughput, and etc. So if this is the architecture or topology you understand, then who affects that, how it affected. So now let me go to the part one, why we need network slicing in 5G and the concepts behind it. Okay, so I will go through the very basics of the what is an access network, what is a backbone architecture, then I will go to all this in detail. So now let me show this picture. This picture is very familiar to you. You know that. Let me go from bottom to the top. This is in our hand, one of them. Maybe a phone, a satellite communication phone, maybe a mobile phone. This is a mobile phone. This IoT connected to here. This may be 5G base station, or this may be a Wi-Fi base stations. And the ADSL lines. These are the landlines. These are the wired lines. And these are the optical networks in a optical fiber network inside a data center, or some of these labs have optical networks. So if you look at, there are two wireless are there. One is this may be 5G or this may be Wi-Fi, and this is satellite. And satellite we are not talking at all, because it's pretty bit rate is low at this present conditions, and also it is a very high delay. So we are talking about this one. And this one is the access network. We call it as access network. Okay. And see, this access network is connected, and this part is only 5G. Please try to understand. And this is the IP backbone. 99.99% or 99.9% is optical network across the globe. Only 0.1% which I left is satellite backbone maybe, but majorly 99.9% is optical backbone. So most of the times when you are communicating, you are going through the optical backbone. And this IP backbone this is called global internet. That may be a metropolitan area network, national backbone, international backbone, and all. And then that backbone may be connected to a data center cloud. This is our cloud. This cloud may be in the same city, maybe in the different city. You are sitting in the Rourkela, then the cloud may be in the Delhi, it may be in the Calcutta close by, or it may be in Bhubaneswar, or it may be in California in US, in Google Clouds. So in this cloud, if you look at, you are a media server, if you are from a Hollywood, you are downloading a movie. Look at this. I am here in a laptop connected to the 5G networks. I'm going across the whole world. That is around 14,000 kilometers from here to reach to the California. From there, I went to Hollywood, and from here, I'm downloading a movie. And I want the movie to be streamed without any problems. For an example, I'm just saying, or you are in a web server downloading something, and all these servers are there. So what is this? This is called access network, regarding which 5G is only and only worried for this part, access network, 5G. This is optical backbone. And this service network in the data center is not a wireless network. So 5G is not at here. It is a completely optical networks, and it is or copper of a Cat6 or something very highly sophisticated copper networks, which is here inside the data center. So please be clear that 5G is only here. I will come in a detail more picture. Okay, so 5G is here or Wi-Fi is here. So now before I go into it, then I will explain you this little bit, because you should have a completely feeling in your heart that, hey, when I am sending a packet from here to any part of the world, what are the networks I am crossing? So you are crossing access network, core network, and a service network inside a data center to download a movie file or a web page, or you are booking a tickets or anything you are doing. So now look at this. This is a very interesting figure which I am showing, because this backbone, when I am saying if you are going out from here to the California for an example in US, because that's the farthest away. So I am telling you half of the world you have to cross. So I am giving this example. In India, what I have to cross, I am sitting at say here, and I want to go to say California, and say then what will happen? I go to Bangalore to Chennai. And I showed you this one because this I'm favoring any companies, but BSNL has a maximum number of length of the optical fiber in India, and this is connected to the NKN. So let me give you some additional information. These 7 nodes, what you see, we call it as super nodes of this country. And these super nodes are designed and long back. Actually, I was involved for the NII 2.0, National Information Infrastructure 2.0, when these super nodes were interconnected more aggressively with the fiber. It was in 2013 and 14. I was a vice chairman to design these topologies. So and then in that topology, we have 7 super nodes, and we are planning to bring in 2 more super nodes, one in Bhubaneswar, another is in another place. So now then so we have 28 states. 28 minus 7 is 21. These are the 21 states. You can see 21 states capital. So please try to understand these 21 states are, each state is connected below them to their districts. Say Odisha, if it is there, Odisha has a district, so this connected to districts. Below the districts, there will be taluka and the blocks. It is connected from there. And from there, it is connected to Gram Panchayat to connected to the villages. There are 6 lakhs villages connected by these networks. This is NKN has National Knowledge Network, which is connected to the NIT Rourkela, all the IITs, and we are also connected to IIIT Bangalore. But the part of the NKN gives to the something called in Odisha, if you Google something called OSWAN, Odisha Statewide Area Networks. So this architecture is there for every state. Okay. Why I'm showing? Because when you are sitting inside the NIT Rourkela, if you throw a packet, it goes through the NKN networks, and from the NKN network Rourkela, it goes to the Calcutta, and from Calcutta it comes to the Chennai, and from Chennai it goes to the international backbones. Okay, so this international backbone has 2 parts. I'll come to that. So now, and this project which is going on for your country will feel good because of all the rural India and all will get connected. It is a 73,000 crores project for 10 years, and the government of India is working on that along with the states. So now when you want to go to here is the California in the United States, and you want to go here and to download the movie. And now look at this. You are in India here. You came out from here from international backbone. Look at this. Why I am showing these figures? You should have a feeling that I am simply touching on my screen, go and download this movie. See how much distance I am covering. I am covering from here to the base station, from base station to these backbones to I have to reach here. To reach there, I have to cross this from here under the submarine. This submarine is going under the Pacific. You see in the Pacific, this side you are coming out, Pacific Ocean, you are coming out, you are landing up in the LA, Los Angeles, and you are going there. So how much distance I covered? I covered close to 16,000 kilometers to reach here. 16,000 kilometers doesn't happen, but I want delay in milliseconds. So those are the things are the demand from 5Gs. I'm asking 5G to give me this, but 5G is only last 1 mile. How to get that? So you have to be very clear on that. So these 5G requirements need a flexible 5G architecture to accommodate diverse use cases and services, that is 1 millisecond to 2000 millisecond. I have a pretty diverse applications, which is I need an architecture which is flexible to support me 1 millisecond, or if my application says 300 millisecond, it is ready. It has 1000 millisecond, it is ready. 2000, my application will tell the network, hey, I need this, you give me. But you see, look at practically how much distance I am covering across the globe to reach to your destinations. So if I want to cross, then I need a network architecture which is flexible. Please look at this. I made a blue color knowingly that the flexibility. What is that flexibility? That means present network is not flexible. No, it is not flexible. It is rigid. I will show you where it is rigid, and you will be really surprised to see. And you know those things, but today I'll put in your brain that where it is rigid and why you want to make flexibility. The moment you want to make flexibility, you will understand. The next moment we will understand to achieve this, network slicing is required. That is to get this flexibility, because I have to this much of variable things. Same rigid networks or rigid, not flexible network cannot give me this kind of 1 millisecond to 2000 millisecond kind of services. So let me go one by one. So key 5G use cases and requirements. So this one I have already shown you in my first slide in the introduction. The EMBB means enhanced mobile broadband, which ITU has told about that. This is 5G PPP, public-private partnerships. So 5G, it is also 3G also talks about that. 3G, 5G people get confused, but still today people call 3GPP because they are habituated to call that group 3GPP, this ITU group, because from 3G standard point of view. In 4G also we called it 3G. So still today people call it 3GPP. So 3GPP is the standard body of the ITU, which takes care of the standardizations of EMBB of the 5G. And these are the three use cases which I have told already: enhanced mobile broadband, massive machine type communications, and critical communications like ultra reliable low latency. And this is a very familiar pictures which you might have seen before. And now also you can see is that if I have taken one example, say critical communication. Critical communication means the last one, your LLC. So in the critical communication, latency is latency is the highest priority. And in case of reliability, highest priority. And if you are a very high mobile with the mobility, how to get these two? So this take care of. Mobile broadband, this green color, you can see data rate, user data rate, spectrum efficiency, and power efficiency, but it doesn't talk about so much reliability. It doesn't talk about so much about latency. Machine type communications may have a connection density, means billions of devices will be connected. This is that. So what we learn in this is that IoT applications, according to their requirement, belongs to one of these three categories. IoT can belongs to all of these three, but your mobile voice and video will come under only one of this, not others. But the moment you add into a mobile any IoT applications, then it will be any of these three. You may be critical if you, or you may be not critical, and all those things. So let me deep dive a little bit on new use cases and why flexible architecture is needed. That word I told you, the flexible architecture, and how this from flexible architecture I am going towards network slicing. So let me explain to you. So use case can range from general broadband access with a global coverage and specialized sensor and extreme mobility. So any use cases, general broadband means I am doing a video conferencing with you. These are general things, sending an email, watching a movie and all. But a critical kind of thing means like a patient is going, a heartbeat is going, and specialized sensors there are delay and any loss and highly reliable low latency is required. A robotic operation. And also these kind of things like extreme mobility, your driverless car moving very fast, but it has to be high reliable communication and low latency, very low latency. So these has changed the world, these requirements, starting from your email to your heartbeat communication, medical communications to driverless cars. The utter difference, now look at this, the utter difference between use cases demands heterogeneous requirement from the networks. What is that? What is this utter difference? From 1 millisecond delay of your this one extreme mobility, that is your driverless car. Because why I'm saying one millisecond, please let's try to understand. You are going to your office, you are sitting behind, and on your laptop you are sending emails and receiving, and the driverless car means no driver, it is going by its own. And India, it is everything is possible. Just imagine India, if you are a driverless car, only God can save you. Anybody can come from the right, anybody can come from the left, anybody can jump from the top, anybody from the manhole can come out in the middle of the road. So I jokingly tell to my students, so the car has to be extra smart than anywhere in the world, if it is in the India. So within a 1 millisecond, the communication should come to me, my car, from the side sensors and from my nearest base station. Hey, somebody is running towards the road, so you stop the car. Why 1 millisecond? Because brake is a mechanical. Brake takes long time, 1 to 2 seconds to stop the car, or more than that. So communication will be 1 millisecond, brake will take 2 seconds, so then car will stop. So these are called extreme mobility kind of conditions. So the utter difference from 1 millisecond to 2000 milliseconds, the utter difference between the use case demands heterogeneous requirement from the networks. And previous figure, that means I need heterogeneous demand from the same network. Same network means I have the same base station as physically, I have the same routers in the backbones, but I am asking them give me from 1 millisecond to 2000 milliseconds according to my requirement. So this cannot be satisfied. This kind of demand heterogeneous cannot be satisfied. I cannot satisfy the present condition because it is a fixed kind of protocols and topologies. One size fits all architecture. That means this is that rigid architecture. It is a rigid architecture I call one size fits. I have given you one architecture. you manage 1 millisecond to 2000 millisecond of delays of different applications in that. So in next couple of slides, I'm going to explain you, which is very much why it is a problem. One size fits. Till today, I am talking to you, I am using one size fits architecture. Means any kind of application I do, I have to use this architecture. One size. What is one size architecture? I made it in a reddish color because it is the danger today. So you have to solve this problem to move to the 5G. So then please be when I'll be telling this one size fit all architecture or rigid architecture, you will understand what I am talking about. So now, keeping above new requirements of use cases in mind, alternative architectures are proposed and R&D to be done for the next. So why the present network protocols cannot support 5G? Let us have a very conceptual discussion, very conceptual, why the present network protocols cannot support 5G. Or why means 5G demands from 1 millisecond to 2000 millisecond variables. So this one size is now why the present network can't. Look at this. I'm going back to our very basic fundamentals. You see, I am talking to you now. It looks like this is my and this is me. You may be sitting at here on some of the servers and all. Look at this. So there are if you go to IETF standard, not OSI standard, according to IETF standard, network has 5 layers. And if I am speaking at here and just look at this. This here heading, it is written layering structures. Of course, you know these layering structures of the networks. I have written in applications layer is in the IETF standard. Applications layer is a merger of application, presentation, and session layer merged into one layer called application layer, and transport network, data link layer, physical layer as it is there. So OSI standard 7 layer, but IETF standard it has merged the top 3 layers to one layer. So it is 5 layers. So this is a logical communication. Look at this. So when I am talking to you, you feel I am saying to you straight away in the applications called video conferencing, and as if it is end-to-end application to transport and connected to your transport, and this is coming to here. Or if I am sending you an email, it is straight away coming from me. Email I wrote, I send, it comes to your machine. Go. This is a logical communication. Please be careful at it. It is a logical communication, and it is not showing practically how it is moving. Look at my next slide. Look. This is written physical communication. This will make you fundamentally clear that practically how a information move from source to destination. Look, this is the application. I am sending an email to a Gmail server. Look, this is going all the layers I cross in between all the routers. Then I reach the destination reach and I can see it here. If I send an email to your machine, it crosses from application, transport, network, data link layer, physical layer, and comes out by the transmitter, enters here in the receiver, goes up till the network layer, come out. Why I am showing you all these things? This is a big question. If you understood this, then next slides onwards, I will make you understand what is called a rigid architecture, that one type architecture fit all kind of application. Whether I am doing a voice call with you, packet moves like this. Whether I am doing a video conference with you, packet move like this. Whether I am doing a medical kind of emergency information transmission to the hospital, packet move in the same layers, application, transport, network, data link, physical goes out like this. And these one router I show for the reduction of the complication of the figures, I can put hundreds of routers from here to destination. From here to Rourkela, I may be crossing 20 routers at least to reach the destination. So this every router I go like this up and down till I reach the final destinations. Having said that, please see what happens next. So now layering structure of the network here, you know. So here I am showing you that 5 layer to the 7 layers because just to make you understand, these 7 layers are from the OSI standard, open standard in kind of things, International Standard Organization, ISOs. So application, presentation, transport, network. I have made this one a blue line here, blue line. All the standard protocols of these top layers is done by IETF, Internet Engineering Task Force, IETF, written at here. And networks layer to the applications layer protocol standard is their monopoly. No one is allowed to touch there. They are the boss. Okay. And bottom 2 layers is now under the control of 3GPP, which does 4G, 5G, and 6G is coming up, and Wi-Fi, Ethernet if you're using, then IEEE. So most of the times we see this one because we work on physical layer, or I work on data link layer, you work on physical layer. So we are most of the time, and here the rapid changes are happening. So look, now please see. Now look at this. This one in the transport layer, there is only two protocols, TCP or UDP. We are allowed to pick up one of them, either TCP or UDP. Only one of them will pick up, only two options. And if I have a voice call, I pick up UDP. If I'm doing any kind of other, 85% of my internet communication picks up TCP. And congestion control algorithm, if I'm picking up TCP, same protocol. Everybody's laptops and mobile handsets, maybe cubic now, previously to Renault and Renault's kind of algorithms. And so one algorithm for congestion control for 1 millisecond delay, same algorithm for 30 millisecond delay or 1000 millisecond delay, only TCP or UDP. Now look, network layers, OSPF or BGP, one of them you have to pick up. And so OSPF open standard path first, and this is the BGP border gateway protocols if you are going between two autonomous systems. And now bottom two layers are changing rapidly and optimized. Data link layer, physical layer, last 10 years, a lot of research is happening on the file layer and the data link layer, and these two layers are optimized according to your application or physical layer conditions and all. And MAC protocols are also changing very fast. You must have seen in the Wi-Fi or 4G and 5G and all. But these top layers are not changing. Network to applications layer. But if not changing, I have shown you that figure, this figure. You see, you are crossing all the layers. You are not only in data link layer or physical layer. Got it? So now I am coming back here again. So only two options, TCP or UDP, only two options, OSPF and BGP. Only when I have to pick up only one, practically one options. Then bottom two layers is changing, but tops are not at all. So same picture, I am borrowed to the next slide. This picture I borrowed to the next slide to make you understand that what is our next 10 years of research. Next 10 to more than that, what is going to do? This next slide is very, very fundamental. Now look at this. Now I am layering structure of networks, which was like this. Vertically packets move from top to bottom. So now this I told you from all the standard protocols done by IETF, these top layers and bottom two layers are by the 3GPP and 5G. Now look at this. The transport layer has only TCP and UDP till today. Other protocols are still coming up. MPTCP, SCTCP, lot of work is going on, but still it is not being so popular like TCP, and only one I have to pick up from here. If I pick up TCP, same congestion control, only one, and OSPF and BGP there, and bottom two layer is rapidly getting optimized. But now look at this, what I've written. Upper five layers not optimized with applications. Why? Because if I do voice, I have to use same presentation layer, sessions layer protocols, and transport layer, maybe UDP or TCP, one of them. For 1 millisecond delay, one of them, TCP or UDP. Whether 1000 millisecond delay, I have to use this TCP or UDP. And on the routing also is one option, OSPF and BGP. So that means I have only one protocol available, TCP or UDP, to pick up to any kind of application I am using. I am invoking from my mobile handset or more from my laptop, from my IoT devices, anything. But I have no other options. And do you think this one will give me those delays, 1, 2 millisecond, 10 millisecond, which is I am demanding from the network? Absolutely not, because they have been done 1968. They have been finalized 1969. It was deployed. Just 51 years completed in internet. And at that time, there was no real-time communication over the internet was there. So this one size fit, which I told you, is a problem. Huge problem. Huge problem. I can't achieve that. Then how to achieve it? This is, see, then vertical optimization is needed. What is vertical optimization? I will explain you in the next figure. That is called the understanding the fundamentals of the network slicing. So now look at this. I want Aadhaar. Delay 30 millisecond. What is 330 millisecond Aadhaar application? You know, all of you know Aadhaar because you are from all of us from India, so you know Aadhaar. Aadhaar, I can tell you, Aadhaar has two databases. One is in two parts of the India, so I know that where it is, but I'll not tell which cities. But let us assume I'm in the southern part of the India, and it is in the northern part of the India. It is there. But so if I want to go to that database and I want to bring back my information, I am standing on a queue in airport where I don't have to carry my identity. I put my fingers on a device which will take away my identity to straight to the other database and bring back. So maximum my security in the airport will allow me to stand there for 1 second. In the 1 second, I have to do 3 activities. One, my biometric has to go from my device to the other database and come back. So round trip time. So that is called my transmission time, communication part. Then after reaching the other database, I have to search from 1.5 billion people databases. My 1.35 billion, sorry, 1.35 billion people. My Aadhaar, that searching has a time. So and that is a 300 milliseconds. And after everything come back, that is a electronics device display on the screen that takes a 300 milliseconds because display is slow. It is a LED kind of bulbs and all. So for communication, I have written 330 milliseconds. If I divide the 1000 millisecond, means 1 second, divide 1000 milliseconds by 3, it is 330 milliseconds. That is end-to-end delay, going and coming back. So now these layers will change. Please look at it now. Now look at this. Application layer protocol. I have to find it out for Aadhaar. Like your browsing HTTP is there. Similarly, equivalent of HTTP or something else, that is called application 1. If I am using TCP, these common TCP will not work because I need to meet 330 milliseconds, a TCP1 or UDP1. Routing protocol, something I have to invent, and MAC1 and 5 for this Aadhaar. And these has to be, please listen, this top to bottom has to be optimized. Now our research is only these two layer optimization. When I was student, it was not there. Only 10 years back, now present students all work on this optimization, these two layers. But I have to do from application, presentation, sessions, all those layers has to be optimized for each applications. Or a set of applications which want 300 millisecond to 350 millisecond, 50 millisecond, they will use this set of protocols. Now look at this. If I have a driverless car, I'm going through the same internet, I have to invent driverless car application 2 protocol because it's a 1 millisecond delay. This is 330 milliseconds, huge difference, 300 times. So for application 2 protocol, TCP2 or UDP2, routing protocol 2, a MAC2, PHY2, these are different. You see routing protocol 2, routing protocol 1. Here there is a no 2 protocols, only one I used to get. Presently I'm getting only 1 protocol for my routings. Here I have a TCP1, TCP2. This is TCP only. Now 2 protocols will be there. So now it is top to bottom optimized. Similarly, 50 milliseconds of a video games, there will be 3. So if you look at this one, this will be inside the same internet or the same device, you can say, but all these devices will have its different sets of protocol for according to the different applications and requirement. This one is what you see vertically, it's like a 1-1 slice. Please listen. This is one slice, this is another slice, this is another, but all together will be in the same machine. When I invoke in my application Aadhaar, this one will invoke, and this one can guarantee me 330 milliseconds. And if I keep my mobile, it works in my car as a driverless car in my mobile. I want 1 millisecond. This is my protocol stacks. This is my protocol stacks for games. So this is called vertical optimization inside the device. Looks like this, but when you see any pictures figure, they show you horizontal pictures. No, inside the device they are like this. For that only I wanted to show you that figure which I drew for you, that you can understand easily this figure, that practically you move from all layers. Look at this, and you reach the destination. Similarly here also you will move through all the layers to cross your packet. You will move from here to go down and go out for Aadhaar. This one, so it has to be top to bottom optimized, and this research is going for 10 years. If you have it from application layer to file layer, I have to invent something and optimize that. It is, I'm sure I will get 330, 1 millisecond or 50 millisecond. A lot of research is left. So this is the genesis, the bottom of the slicing characteristics. So this is called vertical optimizations. So now I will move forward to tell you that how it looks like. Look at this. I am simple example. I am going from here to Chennai, one destination from here, or I'm going from here to Rourkela to any of the machines. So now look at this. This is called inside my campus. This is called intra-autonomous systems. This is called inter-autonomous system. I'm going, but you always look at that vertical picture I showed you, because in the router I'm showing you router, but I'm crossing all the bottom 3 layers: network, data link, physical layer. It has to be optimized to give me end-to-end delays. So like this. So now, if I go from source to destination like this, from India to US or India to from Bangalore to Rourkela or any parts of any of the world, then if you do a delay calculation, these are the for students and for the young people like us, all of us, to understand delay calculation is the major part of our any performance evaluations. It has 4 elements: queuing, processing, Transmission. Queuing means any packet comes to your router, it has first to stand on the queue, then starts when you become the head of the queue, then processing start. That means your protocols, this picture, please try to understand these protocols inside the routing MAC physical get activated in the moment you come to the processing here. Okay, so processing, after the processing is done, then it is transmitted. These three I made it red in color because these are variable. Because queuing delay you cannot predict, very difficult to prediction. Lot of theory gone in. If you start reading from the book of a lot of queuing theory books, and then you can see that. And the processing protocols, every protocol is different. 2G, 3G, 4G, 5G, all protocols, Wi-Fi, everything is different. Processing times, transmission, bit rates are different because of the physical transmitter receivers are changing. And the propagation is the only one I kept it green because it is constant. Because once you are thrown into the medium, if you know the medium properties, that never changes till that. Hence, each layer. So if this is a variable and particularly processing, hence each layer protocols to be optimized from applications to physical layer with respect to requirements of an applications. Each layer has to be optimized to give you end-to-end delay. And propagation is constant. Hence lots of research needed in all the other three elements, queuing, processing, transmission of the delay mentioned above. For quick examples I gave here, if you in a Bangalore and server in California, only one way, only propagation delay is 5 microseconds for 1 kilometer is 14,000 kilometers. I Googled, find it out the distance through that. It is 70 millisecond only for one direction. And from Bangalore to Aadhaar server, so this is, say, if it is in, assume that it is in Delhi, then it is a 2000 kilometers, 10 milliseconds. So these are the only propagations. But if you add off these, it will be very, very difficult for you to meet this kind of targets. 50 milliseconds for the gaming, this one and all. So coming quickly, that to reduce the delay in the virtual circuit switching, MPLS, SDN, software defined network, many research has been done, but not enough yet to meet the required delays of 10 milliseconds or 20 milliseconds of kind of things. So now I make you understand what is called slicing in my previous slides, why I need slicing, and what part 2 is the duration of 5G, how to achieve network slicing. So if you look at whole world is moving in the academia and industry has proposed for the 5G systems and architecture two concepts, evolutionary view and service oriented view. Evolutionary view and service oriented view, let me quickly explain you these two views, how to move, because there is a huge drastic change has to happen on the access network and on the backbone. So evolutionary view says it's a natural transmission from 4G advanced, which we call as a 4.5G, and focusing on significantly improving the efficient mobile networks from 1,000 times the traffic volume or 100 times your devices you can add up under your base station or Wi-Fi, 100 times of throughput, 100 times of delay, spectrum efficiency, 2G to 4G, 30 times your spectrum efficiency already happened. In the 5G coming in, it will again multiple times, it will increase. So these are normal process, natural transmissions. But people are telling, no, this is not enough. Let us go for service-oriented view. What is service-oriented view? I demand 1 millisecond delay for my driverless car from the network. Same network, robotic operation is happening where the demand is 5 milliseconds. Robotic operation, a doctor is sitting in India operating somebody in the Russia. So robotic operation is happening. And there is an email, 2000 milliseconds. So same network architecture, but I need different set of protocols for giving service-oriented view. Service-oriented now, application-oriented or service-oriented. It requires same physical infrastructure of network to take different forms depending on the service requirement. Naturally to the network slicing. I showed you that network slicing vertically, those are the service oriented. Aadhaar 330 milliseconds, driverless car 1 millisecond, video games I'm playing with my friend 50 milliseconds. So I verticalized and make one slice inside the same routers, same devices, physically the same, but inside that protocols are different and they have been optimized, completely optimized. So same physical infrastructure of network, but that will give me different performances. That is the beauty of the network slicing. So service-oriented view required for radical rethinking of existing mobile and backbone network architecture with more flexible. Now, same device, same architecture. If you look at from the top, it looks the same router, same base station, but it is giving me more flexible and programmable network systems to give me according to my applications and requirements. The above possible by leveraging new technologies like software-defined networks and network function virtualization. So these two are the very fundamental coming up. But what is inside that I will explain you. What is software-defined network? What is network function virtualization and management and orchestration operations and all? These are all classical things. We have been working from 2007 on these areas because I took Asutosh's name, and Asutosh and me was to work from 2007 from different projects called IP Multimedia Subsystem for the network management. At that time, it was the first IMS lab we developed here in our campus, but at that time people laughed at me what I will do. But now if you look at 4G and if you go to 5G, if you give a Google and find out SIP, session initiation protocol, network orchestration, now people are massively using those kind of things. So the above possible by the leveraging new technologies like the software defined network and network function virtualizations. How it will work, I will show you. So before I go that, this is the classical picture which you'll find in many literature, network slicing. Look at this, smartphones, same architecture. You see, if you physically look at these three pictures, this net same router, colors are only changing, blue, red and all according to the part of the slice or networks nodes and all. They look, see, this is a ring connected by trees, architecture like that. Look at this. Same architecture topologies, but they are for different requirement. The smartphones, particular delay, they have RAT stands for radio access technology, the different kind of protocol sets fit here. Autonomous driver, that 1 millisecond delay, same architecture giving different kind of performance. And massive IoT, different kind of for a temperature and all, I need 2000 millisecond of delay, no problem. So this is the slices of protocols inside these physical architectures. Okay, so now let me go forward a little bit. This is a classic figure of an SDN architecture. Look at this. Here is you, and here is your friend. You are doing video conferencing. And video conferences data part, the voice and video is here, will go across and go and reach here, and he is telling something coming. So this SDN has divided the network into two parts. One is called SDN controllers and other one is called SDN data plane. This is the data plane and this is the controller. Please listen carefully. I'll give you an example because I am a teacher like your professors and all. Always I love to give example before I explain to my students. Look at you. You are playing football, okay? And you are running to catch the ball and strike the ball to the goal post. So we have two legs, so you are running very fast to catch the ball. So I saw the ball is around 10 meters away from me, and I have to run around say 20 kilometers per hour, that speed, to catch the ball. So who gives the command to my legs? My command comes from the brain. Legs doesn't have the calculations that 20 kilometers per hour I have to run. That is not there in the leg. My brain tells to the leg, hey, you run, then other person before coming to the ball, you can catch the ball. So you calculated looking at the distance and the ball and all, and you started running 20 kilometers per hour. Then you reached to the ball and you stopped on your right leg. Brain gave a command, stop, right leg. Then left leg you kick. Then you kick the ball to the goal post and the goal happened. So you two legs, first running, command came from the brain. Next, when you reach the ball, right leg stopped, given command by the brain, left leg strike, another function, and you went and you strike the ball to the goal post. So this is the brain of the network. This is called SDN controller. All the applications means running, then stopping by right leg, left leg striking the ball, three different applications. And this is my leg. This is my leg, muscles of the leg. And I am running. When I'm running two legs, they are doing the same functions. But when I stop, right leg stops me, and left leg I just lift certain height and kick the ball. Different functions. So look at this: two legs, two different functions, given command from the brain. Similarly, this is the brain called software-defined networks, controllers. All the applications will go here. It will tell, this is your muscle power. These are your switches and routers. They don't have the thinking, but they will give you the power, muscle power, that how much CPU, how much bandwidth, how much memory I should give to this application. When one application will reach here by 10 millisecond, another application invoked by another person will reach here 50 millisecond. And same EUE may be invoked, another downloading he is doing to watch a movie later on, which may take it to 300 milliseconds. Got my point? So this is SDN is the brain, And below that, what you see, the muscle power is given by network function virtualization. Why network function virtualization? I'll explain you in the next 2 slides. That is your muscles, same muscles doing 2 different functions. Okay. So now look at this. So this is called NFV network. So this same box, physically hardware and software, doing the switch, router, load balancer, firewalls, antivirus, intrusion prevention, intrusion detection systems, and all are inside this. And according to the command, this is in your SDN controller. According to the command, this boss will give the CPUs, or that is called network processing unit instead of computer processing units, and the memories and all kind of things to do the functions. Look at this SDN controllers. This is a switch symbol. Look at this previous slide. This is a switch symbol. This is a router symbol. This is a firewall. These are SDN controllers, and this is the same box giving me hardware and software by NFV controllers, and SDN controller give the command. According to that, part of the CPUs, part of your memories, part of the bandwidth will be allocated to your all applications. Like I told you, I'm running my legs, or my right leg stops, the left leg kicks the ball. All this command from the brain, it will come from there. So this is called SDN and NFV functionalities together. So this is the paper which we also did, which is a very complex work, because in the wireless, if you look at here the bandwidth are wireless, and here this backbone is optical, and I have a wireless SDN controller optical, but here your carrier your wireless, here is optical. The mapping is required. So one of my papers from the labs, all credit goes to the student. Please try to understand. I am not taking any credit. This Debabrata used to work, and Jyotsna is my colleague, Professor Jyotsna is colleague. So both of them worked, and this paper is one of the very nicely, we mapped this one between the SDN controllers to map end-to-end delays. So now this is the project which I was telling you in my starting, is this, that which you have recently got on around 1 month back. We got the later, but last week we got the funding, and this is mainly, it is a national mission. You can see here, national mission for interdisciplinary cyber physical systems by the DST. This is a national mission oriented project, and we proposed, actually myself and my colleague presented this one in front of the committee, that mainly we are proposing a 5G base station called 5G Open Radio Access Networks architecture, and it is very, very beneficial to the India, because we are coming out with a new, this is a new architecture which has a open interfaces. These interfaces are like this: loop 1, loop 2, loop 3. That means, if you let me go from bottom to the top quickly to make you understand, this is your ORU, low physical layer. This is your connected RF. Then this is by open one is connected to, this is your higher physical layer, then the MAC, then RLC. This one is worked by one of my colleagues. This is here we are working, my lab is working at here, our lab is working at here, and we are inventing these slicing protocols which will be integrated at here. So what is the advantage of this? Because you see, if you look at the world, there are only 4 companies who dominates the whole world base station. As a result of which, there is a huge monopoly. I don't have to take the names, you know the names, because so that are one of them is the root of all controversy. So Government of India asked, when I presented, they were very happy to see that we are coming out this architecture where we want to work, that which we can produce a different layered structure, and we'll give you open interfaces where if you integrate and complete base station can be done. As a result of which, if we cannot develop this part of this higher layer or any machine learning based or intelligent networks, anything, and any startup of India can do that, or anyone who can do that, I can have open interface to integrate to my this Macs and all. So complete base station can be done in India if 60% is done by the academia and 40% done by the Indian startups and all. So we are breaking down into a different layers of the base stations, which is nothing but low-fi, high-fi, physical layer, MAC, RLC, radio link protocol, PDCPs, RLC, PDFP, and this is completely ML training host, data lakes of the different data are coming in, and this is you can see server orchestration and management. These are all different layers, and these are the open interfaces. And these open interfaces will be standardized. A lot of work is going on now. It will take another 1 to 2 years to come out. Then we can do that. So this is how my next 2 to 3 years of a lot of works will go in. We are as a team together. So this is actually an advanced communication system, TIH, Technology Incubation Hub will be developed, will be the hub. IIT Hyderabad, IIT Bhilai, IIT New Rifle will be working. Government of India has given 150 crores and we are all together working on these directions. So now I'm coming back to the part 3. So now you have understood by these pictures that what is network slicing, how SDN and NFV is going to help, and as I explained to you the muscle powers, how the NFV will give. As I have left with only 5 to 10 minutes because it was 6 to 7. Sorry, I went on explaining you the fundamental concepts. So I will be going into the part 3, the research part. But in the research part, before I go, I'm really grateful. I am indebted to my lab mates, particularly the research students and my all those people who works in the lab. If you, and particularly for this presentation, I took help of part 1, part 2 is there. I have done it, but the part 3 part, this I have took the help of my recent PhD student who joined this year, Sarvari Ravindran, who she has worked and already written 6 papers in network slicing and network sub-slicing. She did masters also here. So I made it in the board. They're all in the network communication research. All these people are in the network communication research lab in IIITB, and there is a strong collaboration. IIITB is this lab and the industry. And I want to watch this gentleman. If you Rajvel Swami, you'll be really surprised. This 3GPP, any 5G security issues. He's the vice chairman of the 3GPP standard body. He's the vice chairman, and chairman is from the Sweden, from Ericsson, and vice chairman and chairman is responsible for any standards to go in the security. And 5G security, whole world is. He's also a student IIITB and also working in Samsung Mobile. Nita Jai is our student. Divakar, he contributed a lot in the standards and Samsung SRIB. Whenever I have doubts anywhere, I go to all these people. Okay, so I go and sit down. They are my teacher. Practically, first 1 year I teach them the concepts. Rest of the 4 years or 3 years, whatever the time they are, I learn a lot. Tushar is the director of Samsung R&D. Sreenivasan Nokia Research Lab. Sarvari NP is in IIITB. Parthivan Intel. He is working on Spectrum. So Anil K is working 4th paradigm in TCP securities. And now all these people are presently in the lab, but some of them have already graduated and they are also in touch with me because I learn a lot from them because whole world is moving so fast. And so I want to give in the names to thank them personally because I only give the talk, but they are the real hero who are the behind the scene. And I am also grateful to Professor Jyotsna Bapat. She takes care of the whole lab and also takes care of all the students. And she herself is a PhD from Penn State and done a lot of works in the Bell Labs in US, and now she's working in the lab. And I am in the bottom in the pyramid because I knew minimum, so I learned from them. So I'm grateful to all of them. So you can find me in the bottom. So coming back, so the architecture of the 5G networks, and if you want to see this, then we are talking about only this part. Please try to understand. This is the radio access network, which you only able to see from your mobile or IoT devices to your base station. But this is called radio access network, RAN. And there is something called core network, which you don't able to see, but this has a huge impact on these RAN's functionalities. And this V stands for the virtual packet gateways, virtual serving gateways, and virtual mobility gateways. These are only 3 servers we are showing. Why virtual? Means all these 3 will be in one hardware, one software server, and according to my SDN command, software defined command, they will be chunk of it will be working for PGW, SGW, and VMW. And then your backbone. You remember I showed you the figures, that backbone, IP backbone networks, international backbone, national backbone, all those of India and the abroad. So this is the backbone. So this much you are doing the research now. And one paper which I showed you, mapping between the wireless networks. When you enter into this backbone, optical network has to do equivalent of research and good research on network slicings to give you end-to-end delays. Please try to understand that. So 5G, what we talk, we only talk about this much. Radio access network, core network, inside the core network, this much of optical network. Small means from your base station to your cloud. Cloud may be 5 kilometers, 10 kilometers away from you, where this core network is situated. In that there is a transport networks. So mainly we are 5G we are saying, but this is very important because there is a wireless domain at here. This wireless is very, very difficult to predict as the quality of service is concerned. Optical side is very predictable because medium is very constant. There is an error and all are very well predicted, but here it is not. And plus there is another challenge is mobility. You are moving from one base station to other base station and you demand quality of service of 10 milliseconds and 50 milliseconds. So this picture is a little more complicated at here from here to here. When I jumped, you can see here I demand the association of virtual machines with the network slice. So in the ORAN, I showed you those orchestration in the top layer, all those things are nothing but SDN kind of thing, activities, optimized resource allocation uses, learning from the environment, interactions across the VM network slice for the resource provisioning and supports. And this is your access network, this is the core network, and these part transportations, how much virtual machines I require for different MMTC, EMBB, or LLC, all this has to be done. And each for functions I need one slice, those which I'll talk to you very shortly. So now 5G components leading to network slicings. If you look at, so this is the this is the radio access network, this is the core networks, these are radio access network R1, R2, RZ, like that. These are the vectors, these are the virtualization of these resources, and this is your transport. These are three networks which I showed you: radio networks, radio resources, core network, virtualizations, and transport. In the optical, how much transportations I get. So these together, this calls functions of RVT. These RVT I need for wireless broadband spectrums. This is my virtualization capacities. This is transport, and these are my challenges. NSP, the function of NSP, network service priority. How every packet is not same. Priority wise communication, bit error rate, BER, and so RER. This is your block error rate. Then TU, user throughput, round trip time, packet drop rate, channel quality. So each application when you invoke from your system, they will demand this. And this demand has to be met by this. And this one has to be done in a slice, because each slice will be defined according to the capacities of this RVT. Then you can meet this. So very fundamental these things. These are the research we have done already in the recent past, thanks to all the students. Research challenge address optimization time duration based resource migration algorithm. So I have a one slice where I have a surplus resource. I migrated it into the deficit slices to give you the quality of service. Efficient handover resources optimization at the users levels. Isolation across the sub slices means if I'm in one sub slice is giving me some quality of service, then I have to isolate that to meet a guaranteed service level agreement. Energy efficiency. If I have a network slicing to meet a 10 millisecond, that doesn't mean I will consume too much of energy. I have to make it very energy efficient for that. Optimization protocol sub slices means I told you the slice, but sub slice means my UE, my mobile handset, one side doing a voice call, other side I am downloading, so I am connected to two different slices. So those are all sub slices of the original slice. So all those things, optimization protocol of sub slices, MAC5 interaction allocated by hybrid automated repeat request kind of things, because we work on Mac, so we have a little soft corner towards that Mac and Mac protocols and all. Adaptable protocol for dynamic scalability and network components, but please keep it in mind, another 10 to 15 years of research left for top to bottom optimization. Only now going on Mac and Phi. Transport layer has to be optimized with the Phi, network layer, data link layer and all, applications layer and all. So like that, every top to bottom complete optimization. System resource allocation for usage of queuing, delay and reductions. So learning based scheduling algorithm in 5G RAN slicing we have done. This is ML based, learning based kind of things. So a couple of problems. If you want, I can deep dive more, but I'll just touch base with you. Some of the protocols we have proposed: multi-objective based NSRP. NSRP stands for Network Slice Resource Profile. So each multi-objective means there are total number of slices, number of users in the networks. You can see here NS and U is total number of users, VI is the number of users within a slice, and also those vectors are N, your virtualizations vectors and all kind of things. So everything, so it is called multi-objective as NSRP. So then I have to optimize the throughput. This UIM stands for the throughput for the cell. Cell means cellular networks. So these are all those parameters required for this. Many people has told me that don't show too much of mathematics. People will lose interest. Only talk about the concepts and the fundamentals. But however, I got little tempted to show you that what people are working in across. So so now I will not go so much in deep. So these are the slices S1, S2, and SN, and these are the NSRP. This is network slice resource profiles for pitch users, and these are your R1 for your spectrums. These are the virtualization. This is for your transports, how much I need to meet B at 10 to the minus 6 to Mbps, B at 10 to the minus 1. Examples are there. So this will be user will throw this much. I need B at 10 to the minus 6 in that B at I need 2 Mbps. Please give me resources according to that. So then you start giving the slices, and you find in this you find this particular user doesn't have a enough resources. So you find out from your complete cellular networks base station which application has a surplus resources. So of core network surplus and or maybe spectrum surplus or maybe transport surplus. So you transfer that to the deficit ones. So these are the mathematics. You can see, you can find this is the delta M is the surplus one. That means if there is a surplus means if I have a this is my used, if I'm using this much, but allocation is this allocation minus the used. That means this is a larger than I have a surplus. Deficit means my allocation is less than my used, means requirement to meet a particular delay. So then this is a deficit. So I will transfer from here to here. So all this calculation you can see related to that. And then if you from surplus you transmit it to the deficit, what is the optimum time? This TDM does for a time. How much time I will transmit? I will give the surplus to you. It is not permanently transferring it to you. You use it, after you require me, return me back my resources. So inside the slices this has to happen. So how many users will be there? This U stands for that. So these are the things, and our proposed algorithm, you can see this blue one is our proposed, is much better than the weighted cell throughput than any existing literatures till today. So this paper is still under the review under the journals communicated. So then these are the results. So which I don't want to. So these are the how many times better than the latest existing in the literatures. And subslicing concept is this novel interactions. You can see that what is subslice? Let me explain to you first. So idea of slicing is powerful to provide a broader consideration of further options and technology and business, which I told you in the previous slides. Subslicing means inside a slice I have to break it down into subslice. Subslice means, say if I have a enhanced mobile broadband is a big slice. There are five mobile handsets are connected to the base station for the EMBB using. So that slice has to be broken down to sub-slice to each of these mobile users, 5 users. But each 5 users may not have the same requirement, different broadband. Somebody is doing video conferencing, somebody is doing games, somebody is doing something else. So those sub-slices has to be there. That is one kind of example. Another kind of sub-slice is, say I'm doing a video conferencing, we're using EMBB slice, but I am also transmitting some data of my body heartbeat and temperature like an IoT device. My mobile will have a multiple senses. So one side I am doing a video conference with you, enhanced mobile broadband, but another slice is massive machine type communication slice. So I am using that part also, say from the same. So my heartbeats are continuously going to my doctor. So then the two major slice, I am getting a part of it from the 2 major slice to my mobile handset. So sub-slicing happening there. So these are the things explained at this. These are subsets of those original slice of the slice to guarantee SL of multiple network slice in slice. You is to get associated with the different categories of services profile defined. So these are the things. So I'll take another 2 minutes to finish this. So this is another paper from the student which got the best paper award in the Connect isolation-based subslices. So that how to protect your subslices by a novel isolation-based subslice for throughput optimizations. You'll optimize the throughput and isolate them from any kind of because it's an internet protocol, so anybody can. So these are the throughput we got and intact. This blue color is our proposed one ISTO algorithm in comparison to any of these existing algorithms. So in summary, if I want to say you is that 5G and beyond systems aims to provide a flexible platform to enable new business cases and models to integrate verticals in industries. Like means it is going to integrate this flexible platform. Why it is flexible? I showed you in those vertical protocols from applications to the physical layer optimizations, and the flexibility. Flexibility means the SDN and NFV will be having those algorithm and protocols which you people will invent one day, and you people will put it there and this will work on that, making it flexible. Now it is rigid. To be honest with you, I showed you what it is. Same TCP, same UDP, same routing protocol, OSPF or BGP, same, no change. If I invoke any application, those are the two options in front of me. But now I need 100 or 50 at least. So 1 to 10 millisecond, one set, 10 to 20 millisecond, another set, like that. So flexible platform to enable new business cases to model, integrate, and vertical industry, automotive, driverless car, manufacturing, entertainment, and all. Network slicing emerges as the promising future-proof framework to adhere to the different technologies need to provide end-to-end connectivity, data processing, and tailored to specific business requirements. The concept of network slicing is designed from end-to-end perspective, end-to-end. Please keep it in mind. We have to do end-to-end. Only 5G we are talking now, but we have to cross all along the optical network. Optical network, inside that I have to make a slices to reach the destination to meet your those 10 millisecond or 50 milliseconds of end-to-end delay. And the spanning across the technical access, transport, core network, and administrative domains, different mobile networks for operators. Administrative domains means I am crossing from one network to the other network to reach the final destination. Include management, orchestration plane. These are the things I was telling you long back. We worked some of those 2007, 2008, around 14 years back, 15 years back. Now people are using it. Now I don't work on these areas because more on Mac and slicing and all. At least a decade of R&D in future, at least a decades of R&D because of this. Top to bottom optimization is needed. Till today, last 10 years, we are doing Mac and physical layer, and some people are working on transport versus physical layer. So they're in the bits and pieces, but top to bottom together has to be done. The ORAN slicing architecture, open interfaces and AI models enables, this is the new architecture which I talked to you, you can Google and see, and enables challenging RAN SLA mechanism to be implemented, which could pave the way for operators to realize the opportunity of network slicing in an efficient way. So this ORAN is coming up where a very quick innovation and deployment can be done, and a lot of people can work on a different area, and they can integrate. No more monopoly of the 4 companies will be there. So for that only many countries like USA, India, Japan, Europe, some countries, except those 4 companies, they are also interested now, are very much interested in this architecture. The architecture is in full blown going on. With this, I thank you all for your patience hearing. Sorry for exceeding by 5 to 6 minutes for my talk, and I'm really humbled that you people gave me this opportunity to speak, and also to the people and participants to listening to me. Thank you again, and I'll go back to the any questions if it is there.
Any questions? Any questions from side?
Posted in the chat.
Okay.
Yes.
Let me go from the top. Thank you, sir. Thank you. Very informative sessions. Thank you. Thank you. Thanks to you all. Sir, in case you are using a pointer, it is not seen. No, I was not using the pointer. I was using the mouse to show you. I think my mouse movement on the screen was visible. Okay. Interesting session. Thank you. Bipin, sir, thanks a lot for a very interesting lecture. Concepts explained very nicely, sir. May I question what is the see more? Okay. What is the criteria for the allocation of priorities in the network slicing for the 5G application? Does any governing body decides the priorities? Oh yeah, very good questions. Thank you very much, Mr. Bipin. And you see, these priorities will be defined by the standards. Standard will say 1 millisecond on delay or 10 millisecond delay or 5. These are the categories, and they will say that these are the applications comes under this kind of delays. So that will be defined by the standards. But before that, a lot of research will happen, and these people will go there and present there. Okay. So and the standard body will decide who will go in front of whom. So that they will do, and then next part, allocation or priorities. The standard will say, and the moment the standard will decide, standard only say that this application this much of delay. How to do that? Standard will leave it to us. So that is the beauty of internet-based kind of standardization. Internet only tells that these are my functions, these are my requirements. Telecom says, hey, this is my requirement plus I want you to do like this. So there is a huge difference between these two. So then there will be a lot of research will be done after the standardization is on the way now, or standardization going on. They will tell us that you meet 5 milliseconds for this application. Tell us very, very tough. Let me tell you, it is actually sometimes we see dreams in the night that how to meet those kind of delays. So very difficult, very challenging, but very interesting. One should do that because you see from 1000 millisecond now people have come down to 150 millisecond. Now when I am talking on a 4G phone to you, it is 150. People have done it, so it's doable. So now, so this research is open. Research is still open. A lot of ML based. Thank you, Bipin. Madhusudan, more informative, enjoyable. Thank you, Madhusudan, for the questions. Very nice session, sir. Chandra, I guess. Thank you.
Sir.
Slides.
Sir,
yes.
hello.
Slides will be with the Professor.
Hello.
Professor Susmita. Slides will be there with the Professor Susmita. If you can write to her with her permission, and it's all yours. Please go ahead. Any questions?
Any more questions?
Virtualization. How does network virtualization play a role in the future wireless communication system? Yes, it's a very nice question. I showed you that picture now, that SDN and NFV. That NFV part and SDN part will be there in the base station or behind the base station, just behind the base station. How? So 10 base station will be connected with edge computing. You might have heard the name fog computing, FOG fog computing, or edge computing, or cloud computing. Inside the cloud, SDN and NFV both will be there. And as an user, I will be holding this mobile. I want a voice call. I started the application. It will go to the base station. Base station will transmit my control information to the controller. Controller will do the those brain and tell the router and switches, do this. That's all. So it will be there. So physically you have to understand where the things are. For that only I showed you so many pictures and how flows happens. Thank you.
Okay.
So
Hello.
Okay. Good evening, sir.
Good evening.
Okay. Sir, my name is Dr. Suman Kumar De. So I have one question over there. So in the optimization you are doing over there in this PPT. So which software you are using to optimize this? It is a integer linear programming optimization of MILP or non-linear. And second thing, that when we are solving the problem, the optimization problem, how many users or nodes you have considered during that?
Yeah, thank you very much. In one of the graphs, it was there. I started from 20 nodes to 200 nodes. And before I give other answers, please let me, Professor Susmita, do you have times, another 5 minutes or something?
Yes, please carry on.
Thank you. Because I have already crossed time, you should not. So nice of you people are generous giving time. So thank you. So let me go ahead one by one. So it has been 220 to 200 we did under the base station with the practical, because we considered some parameters. It is there. All the parameters has been mentioned there in those graphs, and also these are multi-objective parameters. So, and each objective may not have a dynamic by natures according to their properties. So some parts are it's a majority of the time it is not linear, actually. It's a non-linear kind of things. So if they have done, so if you want, if you write to me, I can send those papers to you also. So no problem.
Okay, so then I will send you mail regarding that, because I am interested that actually I was that kind of field in the optical network. So I am interested for that also.
Very good.
And whatever the optimization I did, this is the MILP optimization I did.
Yeah.
So there is a single objective was there.
Yeah, but you on my figure, you understood you have a big role to play. 5G is very complex, I know, because of the wireless part. For that only all of us are into the wireless. It's because of a lot of complex, but optical is becoming more complex demand because a lot of traffic has to cross the optical. So optical has to, that mapping has to be done between the wireless and optical has to do those slicing kind of work, because optical is a mostly very optical. One thing in optical is very good is that too much of muscle power. Means each lambda is around 40 gigabits, and now it is 100 gigabits. So if I have
even 400 gigabits also is available nowadays.
Yeah, no, I will, but I'm coming that because when I was student, it was only 1 gigabit. Now
Yes.
it's 10 gigabit when I graduated long back, and I'm talking about 1989, finishing my PhD at that time, 98, 99. 10 gigabit was just in. So I have a hands-on experience of multiplexing in by hand by around 30 to 10 gigabits in a single fiber. That means and pushing into a metropolitan area network. So I have hands around the year 2000, 2001 I'm talking about. So now it is went to 40, 80, 100, now 400, all kind of things. So optical has that huge advantage. What I wanted to say is that muscle power is huge, push the bits, but still then it will starve because number of users are increasing, rich multimedia is coming out from each users, and how to do slicing on that has to be worked on. That has to be worked on. And routing, fast routing. And I know that a lot of this all optical switches was last 20, 25 years back, a lot of research was done in that. And because OE, these things you know, I don't want to elaborate.
Yes, sir. Yes, sir.
I know. So now it's all optical switching, routing, all things, and along with the QoS, buffering, all optical network buffering, sonar, all those things. Good.
Yes, sir.
Very happy you are working on those areas also, but wireless is still complex. Another 10 years of work, 15 years of work minimum.
Okay, sir. Okay, thank you,
sir.
sir.
This is Suresh here, sir. One question regarding the sub slicing, because I'm trying to, we are trying to work on some application where we need multiple slicing. Is there any place that which is currently available where we can test this or test bed from end to end when you say both on the RF and core side and on the cloud side fully want to do? Because I know that some academics, it's happening, but if you can guide us in this or some pointers.
So let me tell you, this slicing, sub-slicing is a in a phenomenon, is a new phenomenon yet to be deployed and give you a complete test bed in India, particularly. Point number one. Point number two, there is a test bed which has recently come up. It's called 5G test bed by DOT, Department of Telecom, which took the help of the 6 academia, and they have done it. They have done the test bed, but whether that is open to everybody or not, I don't know. But it is there in the IITs or in the when you can find it out. And if they allow you, you can
Thank
go.
Thank you, sir. Otherwise, I will connect offline, sir, in the paucity of time. Thanks a lot, sir. Yeah.
It's my pleasure always.
Thank you, sir, for the wonderful session. Yeah.
Thank you. Thanks to you all for listening. And thanks to professors of the NIT Rourkela, those who have arranged this, because they are the people who should get, they have done the all hard work. I only gave 1 hour talk, that's all.
Thank you, Dr. Das, for this generosity. Today we got the opportunity to listen to a pioneer in SDN and NFB. And he gave us so many detailed research challenges, open research challenges also, that is also exposed the participants new architecture, ORAN slicing architecture. So for the upcoming massive IoT, autonomous driving applications for all society at large applications, this work will be highly beneficial. And as he has got a big project of developing the advanced communication system, I again congratulate Professor Das for that. So
thank you.
Yeah,
I need congratulations. Along with that, I need good wishes for all of you to finish that, because it's a huge challenge and it's a pretty complex ORAN, I know, but long way to go next 3-4 years.
So we expect a lot from you, sir. Thank you.
Thank you. I'm logging off now, and thanks for the opportunity, and have a wonderful time in these workshops.
Yeah.
Thank you. Bye.
Thank you so much.
Thank you. Bye.